Değerli katılımcılar, sevgili arkadaşlar, ülkemizin bilim dostu, bilgisever güzel insanları, herkese iyi akşamlar. Bu akşam yine TÜBİTAK Temel Bilimler Araştırma Enstitüsü'nün matematiksel fizik ve uygulamalı matematik seminer serisi kapsamında bir güzel ve heyecanlı bölüm daha gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Ben de bu vesileyle hepinizi saygı ve sevgiyle selamlıyorum. Matematiksel fizik, insanoğlunun evrenin suskun güzelliğine hayranlığı ve onu merak etmesiyle başlar. İnsanoğlu doğanın işleyişini anlama yönünde ilerledikçe her zaman yeni matematiksel bilgilere ihtiyaç duymuş ve en önemli açılımlar matematiğin verimli kullanımı sonucunda gerçekleşmiştir. Bu durum tarih boyunca pek çok büyük düşünür tarafından vurgulanmış, evrenin temelinde matematik yatmaktadır gibi özlü sözlerle ifade edilmiştir. Fizik prensiplerinin soyut matematiksel yapılarla birleştirilmesi sonucunda öngörülen ve keşfedilen doğa olaylarının uygulamaları muazzam pratik sonuçlara yol açmıştır. Soyut matematiksel yapılarla doğa olayları arasında bağlantı birçok deneyle kanıtlanırken, bu bağlantının nedeni bir gizem olarak kalmaktadır. Bu akşamki seminerimizin konusu da yukarıda söylenenler kapsamındadır. Geçen yüzyılın 60'lı yıllarında elektromanyetik alanları madde ile etkileşimini inceleyen Sovyet Rus bilim insanı Viktor Veselago tamamen matematiksel bir yaklaşımla maddenin kırılma indeksini negatif kabul ederek inanılmaz elektromanyetik olayları öngörmüştür. Fakat doğadaki tüm maddelerin kırılma indeksinin pozitif olduğu bilinirken bu konuya ilgi zaman içinde azalmış ve kaybolmuştur. Yaklaşık 50 yıl sonra bu konu tekrar gündeme gelmiş, doğada bulunmayan negatif kırılma indeksli meta malzemelerin laboratuvar ortamında üretilebileceği kanıtlanmıştır. Günümüzde meta malzemelerin kullanımı elektromanyetizmada yeni ve devrimsel nitelikte ufuklar açmaktadır. Bu konunun dünyaca isimlerinden Londra Imperial College Araştırma Üniversitesi'nden harika bir bilim insanı Profesör Sir John Pendry bu akşam bizim konuşmacımızdır. Profesör Sir John Pendry, meta malzemeler elektromanyetizmada yeni ufuklar açıyor konulu bir konuşma yapacaktır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Professor Sir John Pendry, dear participants, colleagues and friends, a very warm hello everyone and good evening. It is my sincere pleasure to welcome all of you for this occasion of the Mathematical Physics and Applied Mathematics Seminar Series of TÜBİTAK Research Institute for Fundamental Sciences. We organize these seminars for national and international audiences with the participation of distinguished scientists and great speakers of the world. It is also my distinct pleasure and honor to emphasize that we are absolutely thrilled to have with us Professor Sir John Pendry, a great scientist and wonderful person from Imperial College, London. He's going to give a talk entitled Metamaterials, Open New Horizons in Electromagnetism. Professor Sir John Pendry is a leading United Kingdom physicist of international renown. A student of the University of Cambridge, he started his research career with a PhD in physics in 1969 when he became a fellow of Downing College. He left his native England for research position at Bell's Labs in 1972-73. He returned to Cambridge before joining the Daresbury Laboratory in 1975 and eventually Imperial College London, where he has served as head of physics department and as principal for the Faculty of Physical Sciences. Professor John Pendry has a rare distinction among scientists of having established a completely new and unexpected area of research, metamaterials. The electromagnetic properties of materials, such as electrical conductivity, were standardly thought to depend upon the properties of materials of which they are composed. In the case of metamaterials, however, the electromagnetic properties depend upon their structure. This had had a tremendous impact, enabling the identification of new properties not found in nature. Pendry's perfect lens makes use of such a novel property, negative refraction, and is a remarkable example of the revolutionary nature of metamaterials. Pendry has deployed transformation optics to develop a cloak of invisibility that has attracted worldwide public interest. The cloak can hide objects from electromagnetic fields, and the version of this design working at radio frequencies has now been implemented experimentally. Professor John Pendry has received numerous awards, including Dirac Prize, BVC Medal and Prize, Royal Society Bakerian Medal, Royal Medal, the UNESCO Niels Bohr Gold Medal, Isaac Newton Medal, Kavli Prize in Nanoscience, and many others. In 2004, he was honored with a knighthood for his services to science. He was elected Fellow of the Royal Society and Fellow of the Institute of Physics in 1984. In 2013, Pendry was made Foreign Associate of the US National Academy of Sciences. With this, I want to thank once again Professor Sir John Pendry for joining us this evening and invite him to the stage to begin his talk. John, you're welcome, please.
Thank you, Ali Kram. I hope I can live up to that glowing introduction. Let me share my screen so you can see my slides. That should be working now, and I'll go full screen.
Yes,
so
it's perfect.
Good. Whenever you want to do something to build something, of course, it's an obvious thing to say, you have to build it out of some material. So you have to find a material to construct whatever device or invention that you have. And in electromagnetism, it is sometimes the case, in fact, it's quite often the case that we want to do something, to build something, and the laws of physics seem to allow it, but when we look around for the materials to achieve what we want to, they're not there very often. And so this idea of a new approach to material properties, which is what metamaterials is about, has had quite an impact in electromagnetism. So what is this idea of a metamaterial? As I've mentioned, they give access to material properties never available before. They differ from photonic materials in that whereas photonic materials have very complex electromagnetic properties and can do interesting things, but are rather difficult to work with in a design sense, metamaterials can be described simply by epsilon and mu, and this simplifies the design process. And they've also, their design has been enabled by transformation optics, which is a technique I'll say a little bit about. So the structure of the talk will be, first of all, some historical aspects, then some applications, and finally, a look at what's going on at the moment and some practical applications. This for us was the structure that kicked things off. It's the so-called split ring structure. And the idea was to, oh, excuse me, I seem to have skipped a slide there. Yes. Yeah. Okay, so I haven't told you what a metamaterial is, so I better do that. In conventional materials, the properties derived from atoms and molecules. But the things which polarize to give the material its properties don't have to be quite as small as a molecule or an atom. They simply have to be a lot less than the wavelength. So they have to be, whereas the wavelength might be of the order of a micron or a bit less, then the metamaterial structure at optical frequencies would be some tens of nanometers. If you're working at RF, where the wavelength is 10 centimeters or so, then the metamaterial structure will be a few tenths of millimeters. So instead of the atoms and molecules, what we do is to implant in these metamaterials structures which have a local response to electromagnetic radiation. And because these structures have properties which depend on their geometry, and geometry is the number of geometrical designs you can think of is infinite, then that gives you a lot more flexibility in materials design in addition to that provided by chemistry. So we add the dimension of structure to that of chemistry, and we find we can get a lot more materials. Here is one structure that for us kicked off the metamaterial story. It was made by Mike Wilshire, who was then working for the Marconi company. And the idea was to have a structure which generated magnetism without magnetic materials. This structure is designed to work at RF at a wavelength of about 10 centimeters. And the diameter of these rings is a bit less than a centimeter. And the way it works is this. So if you apply a magnetic field normal to this circuit board, that will induce a current around these rings. And that current in turn will produce a magnetic field. So through the medium of having a conductor in the shape of a ring, you can get a magnetic response to a magnetic field, even though the materials themselves do not have any intrinsic magnetism. But there's a little more to this than a simple ring, because if you can look carefully at this structure, you'll see that the rings are split. So the current cannot find its way completely around the ring unless it jumps the capacitance at the end of the ring to bridge that gap with capacitance. So here you have a structure which is in the form of a ring, and therefore it's inductive, but also has some capacitance, which is essential to its function. Capacitance, inductance means it's a resonant circuit. It resonates at about 10 gigahertz. So resonances have a peculiar property, and that is that if you are at a frequency which is well below their resonant frequency, they go polarizing one direction, but as you tune the frequency of the exciting radiation through the resonant frequency, the sign of their response flips. And so this particular structure, if you look at the right frequency, will polarize in the opposite direction to the applied magnetic field. And it was this property which attracted the attention of David Smith, then working in University of California, San Diego. David Smith and Shelley Schultz were at a conference in Laguna Beach where I introduced this concept of a resonant structure. And they were particularly interested in this property of magnetism, which has a negative value for the permeability, because such things are apparently very rare in nature. I didn't know that at the time, but that is true. And what they did is to make a structure, including these split rings. Now they're split squares, actually, but same principle. So here's a structure which has negative mu because of the resonance in the rings, but it's also got a negative permittivity. And if I can show you here, on the other side of the circuit board, there's a copper wire, and that also is a resonator, but that's an electrical resonator, and that too has a negative response to electricity. And this achieves something which was sought after many years before, which is a negative refractive index. And I'll have a great deal more to say about that in a few moments. Since that first demonstration of a negative refractive index, for which these conditions are required, the concept has been pushed to higher frequencies. Here's a so-called fishnet structure, which is made in the Jang group at Berkeley, California. And you see that this dimension is 1 micrometer, and the structure consists of alternate layers of silver and dielectric in the form of magnesium fluoride, which are a few tens of nanometers. So now we're getting towards optical frequencies. This is in fact communication frequencies. Here's a sketch of the structure, and here's an electron micrograph showing what it looks like when you make it. And that structure has a negative refractive index at near visible frequencies. Now, since their introduction, metamaterials have really achieved quite a few things. They can generate giant paramagnetism, so they're not only useful at RF and visible frequencies, they also respond to DC fields. They've been employed in magnetic resonance imaging. They are part of the new 5G technology, and even more so in 6G technology. At infrared frequencies, they're used to control thermal radiation, and at terahertz, they're used to enhance the efficiency of cascade lasers. In plasmonics, at the visible frequency, they are used to enhance nonlinear phenomena, give single molecule detection sensitivity, and giant chirality. Our applications are not limited to electromagnetism. The concept is valid anywhere that you have waves which obey a second order differential equation, and that is true of acoustics, and they've been used in soundproofing in the domestic environment, and in stealth technology in the latest generation of nuclear submarines to make them quiet and stealthy. In mechanics, they can also have materials with novel mechanical properties. Vincenzo Vitelli has designed structures with negative Poisson's ratios. Now, I did promise to say some more about negative refraction. I like this diagram here, which shows epsilon along one axis and mu along another axis. And where both epsilon and mu are positive, as in conventional transparent materials like glass and water, then you get transparency. But if you make one of these negative, for example, if you make epsilon negative, then that is the case in a metal, which has a negative epsilon at optical frequencies. And of course, metals are opaque. You could get the same effect if you made the permeability negative. It would be a sort of magnetic metal, if you like. There are very few of those found in nature. But if you make them both negative, then the wave vector becomes real again, and these materials are transparent. They're transparent, but different. They have a negative refractive index, and this was pointed out by a Russian scientist, Veselago, many years ago in 1968, and he in fact gave us a recipe for negative refractive index. He showed that if the permittivity and permeability are both less than 0, then you have this negative refractive index quality. Now, you might think negative refractive index, why is that so exciting? Why is it so different from any other refractive index? And I want to show you that this subject in negative refraction is a very subtle one. And even looking at the most simple diagram you could possibly draw, you can immediately conclude that something very strange is going on. Let me show you. So here's a definition of refractive index as announced by Snell's law. In an ordinary material, if you have a ray of light shown in red here, incident on some material, then in glass or water, it would emerge on this side of the normal, at a different angle maybe, but still at a positive angle. Now, if you make epsilon refractive index negative, excuse me, then one of these angles must be negative. And here I show the angle going the wrong side of the normal inside the medium. So the light bends back on itself in this chevron shape, which is characteristic of negative refraction. Now, that's a very strange thing and caused a lot of controversy when these materials were first made. And the reason is this, that in the vacuum, the direction that the ray travels in is the same direction as the wave vector. So here in green, I show the wave vector of a ray of light in vacuum, and they're parallel. Now, there's a very powerful law not even in physics, in mathematics, it's required by the translational symmetry of a flat surface. And the law is that the component of the wave vector parallel to the surface must be conserved across the boundary. So this wave inside must have a wave vector which has a projection on the surface in the same direction as this. And if the wave vector was parallel to the ray, then that's impossible to achieve, as you can see. And we're inevitably drawn to the conclusion that in a negative refractive medium, the wave vector must point in the opposite direction to the direction of travel of the wave. And that's really very odd. Why? Well, so here's that diagram over again. Consider a packet of waves moving to the right. So there's the envelope of the wave packet in red, and there's its group velocity denoted by the arrow. Now inside that packet are the waves, and they will have a wave velocity which is opposite to the group velocity. So you have this packet going along. In a medium like glass, the waves will keep pace with the packet and move in the same direction. But in a negative refractive medium, they're traveling in the opposite direction, as if they're trying to escape the other end of the packet. It's a little bit as though, if you can think of the phase of the wave as a sort of clock, which registers how far the wave has gone, then it's as if the clock is going backwards in this particular pulse. It's as if the wave is unwinding the phase. In fact, indeed, it is unwinding the phase. And we'll come back to that concept when I start talking about imaging with these negative refractive materials. Largo knew that his negative refracting material could focus light. He had this diagram in his paper, and because the ray bends back on itself towards the axis, the ray crosses the axis a second time here and a third time here. So once at the origin, second time at the first image, and a third time at the last image. But Largo was very keen to make some of this negative refractive material, but however hard he searched, he could not find a naturally occurring material that had this property. So very frustrating, because although the concept created a lot of excitement in the late 60s and early 70s, it died a death because nobody could make the stuff. And it required the presence of metamaterials before we could actually make a negative refracting medium. Now, Veselago realized that his lens could focus light, but at that time, what wasn't realized was just how remarkable this lens is. All conventional lenses are limited by something called Abbe's law, which means they can't see anything less than the wavelength of light, or half the wavelength of light, something of that order. But Veselago's lens, it turns out, as I pointed out some time ago, if you make it with exactly the right properties, it can be a perfect lens. And to explain why that is so, let me, let's see, I'm going the wrong way, aren't I? Let me introduce this concept of transformation optics. So this is a new way of looking at how light behaves. Now, in the old optics, we have Snell's law, and that tells you how light behaves at an interface. We all know Snell's law, or Descartes' law, if we're French. The two scientists invented it at more or less the same time. And there's a lot that Snell's law doesn't do. We have Maxwell's equations. So why are we not using Maxwell's equations, and why is Snell's law still taught and indeed still used in the design of optics? What's wrong with it? Well, it works in the ray approximation. It talks about refraction at discrete interfaces. It's limited by the material properties. It knows nothing about the wave nature of light. It doesn't talk about reflection at the surface. Nevertheless, it gives us a very, very valuable physical picture of how light behaves in media. And we can imagine using Snell's law, how if we altered the curvature of a lens, for example, how the light might behave under those circumstances. It's very difficult to have that picture just by staring at Maxwell's equations. It's quite a powerful tool, is Snell's law, for your imagination. But these days, we want to do more than talk about the rays of light. We need to look at light on a nanoscale, where the ray approximation completely breaks down. So we did a new vision. And what we did was to replace the concept of rays of light with the ingredients that are part of Maxwell's equations, which are the electric and magnetic field. And these can be represented by field lines. And we're going to control the field lines using transformation optics. And because this is valid, this field concept is valid at the level of Maxwell's equations, then the theory will be valid for all situations that can be described in terms of Maxwell's equations. What is transformation optics? To explain what it's about, let's go to this gentleman who needs no introduction. Before Einstein, people thought about space as nothingness. It was, if you look at words for vacuum, you find descriptions which are searching around to find different words for nothing, emptiness. But Einstein didn't look at the vacuum like that, and he was forced to have a different view because Maxwell showed that light was a wave. And it's a wave that propagates in vacuum. It comprises electric and magnetic fields dancing around one another. But there was a problem. And the problem was that all other forms of waves were waves in something. So you have a sound wave, which is the vibration of air. You have a water wave, which is the vibration of water in the sea or wherever, and so on. But the problem was that Maxwell's equations described a wave, but they weren't waves in anything as far as 19th century science could say, because the vacuum was empty. So how could you wave about something that was empty? And Einstein realized that space was a material, and he described things like gravity and so on in terms of the bending of space. And his way of describing the distortion of space by a massive object was to introduce something called the metric, which simply tells how much space has been squashed or stretched in various directions. Now, it turns out that if you write Maxwell's equations in a space that is distorted, then you find that the metric appears in Maxwell's equations in just the place that the refractive index does. And therefore, it's not a surprise that if you have a massive object, the sun is slightly massive, and if space is distorted around the sun, then it can act like a lens, because as far as light is concerned, it's just a different refractive index. And that was the key test, or one of the key tests of general relativity, that light can be bent around the sun. So when you have to have an eclipse of the sun before you can see this, because the sun's so bright. But when you have an eclipse, you can see that stars change their position in the sky, because the trajectory of the light passing close to the sun actually makes them appear to be in a position that they aren't really in. I say a slightly massive object. Here is a very, very massive object. This is a picture of a gravitational lens mirage taken by the Hubble telescope. In the foreground is an extremely massive galaxy, and it has gravitationally distorted light from a much more distant blue galaxy located behind the red galaxy. And so, although you shouldn't be able to see the blue galaxy, because it's not in direct line to you, you can see the light from it, which is refracted in a lens-like manner around this massive red galaxy. So we took that idea and we thought, well, if you can bend space, then you have to think of space like a rubber sheet. So here I've drawn some coordinate lines so you can see what's happening with the rubber sheet. And here's a field line. It could be any conserved quantity. It could be an electric field, a magnetic field, or it could be the Poynting vector. So that could be a ray. And then if you want that field line to go somewhere else, then you have to recognize that it's glued to the rubber sheet. So when you distort the rubber sheet, you also distort the field line. And when you're done distorting that sheet, you then have the ray moving in a different direction, or the field line moving in a different direction. And from the distortion of that coordinate system, the transformation from this Cartesian system to this complex one here, this coordinate transformation gives you this quantity lambda, from which you can construct the permittivity and permeability, which will give you this ray trajectory here. So I don't have time to give you a simpler explanation. Of course, I want to come on to some applications, but I do want to tell you about one test that we've made of this theory. We wanted to show people just how useful this idea of transformation optics, have been able to manipulate field lines. And the test we chose was most difficult one we could imagine, which was to make something invisible. That's been a sort of dream for every boy and girl who has ever read Harry Potter. But the icon in this case is not Harry Potter, but Peter Pan. And that is because Peter Pan is the little boy who, if you know the story, his story, it's the little boy who lost his shadow. So if you want to make something invisible, it's not enough to get a pot of black paint and paint Peter black, because in a bright background, you can clearly see that there's something there between you and this bright background. And so what you've got to do to make Peter invisible is to get rid of his shadow. And when the shadow's gone, that really is invisible. Now, it's very easy to state what you would like to do to make something invisible. And we wrote this paper some time ago in which we showed how to realize the goal of making something invisible. So here's the idea. Inside this central sphere, doesn't have to be a sphere, it's easiest to draw a sphere though, we have something we want to hide, and it's not got to have a shadow. So around this hidden object, we put a cloak, which is entirely contained within this second sphere here. So in this annulus, you're going to do the trick that makes this thing invisible. And the trick consists of taking every ray of light that enters this cloak, guiding it around the hidden object so it never sees that object, and then allowing it to escape, but being very careful that the direction it travels in when it escapes is the same direction it would have traveled in if it had gone straight through this object. So there's a sort of chicane around this hidden object. Now, I put it to you that using conventional ideas of refraction, that might be very difficult to design. So you might think, okay, I take this ray and sure enough, I can guide it around. I can think of a continuously variable refractive index, and then I can release it here and make sure it goes in the same direction. But that's not the end of the story, because if another ray comes through here, which necessarily traverses the same territory that you've carefully designed for this ray, that design also has to do the same thing for this ray and every other ray that comes through. So that's really quite a challenging problem. It's a non-local problem, and it would take a computer, even with artificial intelligence, a very long time to sort it out. But here's what transformation optics does. It solves it in one stroke. So I start off with the sphere, and it's empty in the first instance. So light will go straight through. But I want to create a space in the middle. So I appeal to the concept that space is a piece of rubber, and I'm going to make a hole in that rubber space, and I'm going to push away all the space that occupy the central region here, and I'm going to squash it into this region around here. Okay, so when I do that, I take with this rubber space all the rays of light that were traveling freely through this region here, and now they're traveling only in this region here, and they never touch this region. You can put in here anything you want. You can have any metric you want. You can put objects in there, whatever. It's a totally disconnected piece of the universe. Nothing can see inside it, providing that you build this cloak right. But look, I mean, you've now got a piece with a very simple geometry, which is compressed here. This is the simple formula for the transformation of these coordinates, the radius is being compressed. And from this, you can calculate what the values of epsilon and mu are for this cloak. And notice what else you've done. Because when you distort the rubber space, you move the rays of light into a different trajectory. The complement of that statement is that if you don't move the rubber, if you don't stretch the rubber, then you don't distort the trajectory of the light. So you haven't done anything with space out here. So the light which was out here, whether it's on this side or the other side of the cloak, is still traveling in the same direction. And therefore, what you've done is to design a cloak which has all these properties for every ray of light that travels through here, because they've all been pushed aside by this rubber sheet. And by the way, it works for static magnetic fields as well as rays of light. Now, that cloak was realized by David Smith's group. And look, I do want to finish my story. And I realize I've got rather a lot of material here. So I'm going to ask you to take it for granted that the cloak works, which it does. And I do want to tell you about negative refraction. So here's the Vesolago lens. And I realized some time ago that not only does it focus light, but you can make it focus light perfectly. And that really created a firestorm in the literature, because Abbe's law that you can't see things much smaller than the wavelength of the law was thought to be an absolute law, but it isn't. You can design a lens to be perfect. Whether you can make it perfect depends on the materials. And there's the rub, you could say. So how can we think about the perfect lens? How can we realize how it may be perfect? Well, remember that transformation optics works at the level of Maxwell's equations. So if we can design a lens not using Snell's law, but using transformation optics, then if we can do it, that will be perfect. And here's the way we go about it. So I take a bit of space here represented by this line, and then I'm going to squash space. I've squashed this middle bit here. Here's a trajectory, if you like, in space. And as I squash space more and more, turns out the refractive index of this squash bit of space, not surprisingly, gets very large. And in fact, if you squash the space infinitely, the refractive index becomes infinite. And if you squash it some more, then you know what the function of 1 upon x does as you go through the origin. It goes from a very large positive value to a very large negative value. So as you squash it through the origin, you arrive at this piece of space here. And you've done something very strange to space, because here this is ordinary space, a bit squashed, but yes, it's recognizable as ordinary space. But what you've done here is you've folded space back on itself. And if you're sitting at this point, there are other points in other spaces which actually overlap you. So this space has 3 manifolds, 1, 2, and 3 at the same point. So space is folded back on itself. And so some light going along goes backwards and then forwards. And in that way, we can understand how the lens focuses, because you may think that the light is going through the lens this way. But what the light thinks it's doing is then forwards. And then remember that diagram with the phase clock moving around. The phase clock reverses and the light goes backwards. And that's why it focuses here, because it passes this point once in a positive medium, twice in the negative medium, and then on the way out again in a positive medium. And that explains the 3 foci, but it does so at the level of Maxwell's equations. So all the fields take part in this focus, and the focus is perfect if you achieve this condition of epsilon equals -1 and mu equals -1. Now, I've been asked to finish about 10 to 5. Now, Alikram, do I have 5 minutes to tell about
please,
some other thing?
Please, you're welcome, please.
Okay. Now, this this lens has been manufactured in an approximation using a slab of silver by the Zhang group in Berkeley. And I propose that maybe, although it's very, very difficult to achieve this concept of ideal negative refraction of visible frequencies, I proposed an approximation to it, and it's this: that if an atom emits light, the light, as I've told, consists of electric and magnetic fields. And the light starts off in this electric field from electric dipole, and eventually over half a wavelength, it will change into a magnetic field and then back to an electric field and so on, dancing away. However, if the light doesn't travel half a wavelength from the emitter, then it doesn't acquire much of a magnetic field. And so if we're concerned with objects which are all of highly sub-wavelength dimensions, nanometers, then you never get a magnetic field of any strength. And so achieving mu equals -1 doesn't matter. What really matters is getting epsilon equals -1. And you can do that because a metal has epsilon, which is negative, and at the right frequency, silver has an epsilon -1. And that was how the Zhang group made a silver lens in Berkeley. So here is the silver lens, and they're looking at some nano grating here and the word nano in a chromium mask. And the dimensions here are tens of nanometers. You can't, of course, see a sub-wavelength image, and instead it was written in a photoresist, and then the photoresist was developed and looked at with an atomic force microscope. And in this way, they're able to resolve a grating with a 60 nanometer period, which is λ/6. More impressive, perhaps, is this word nano, which if you don't have the lens there, you can only see with an ordinary lens this broad peak here, and that's what it looks like in the photoresist. But if you then put the silver in space, it's like putting your spectacles on, and the whole thing comes into focus again. So that was a demonstration that this idea can be made to work in practice. So I was going to finish there, but since Alikram has kindly allowed me a few more minutes, I do want to move on to applications. Sorry to rush things a little bit, but I think it is important to say what metamaterials are useful for. So metamaterials have been applied, they've been around for 20 years and more. And in that time, people have thought of a lot of very interesting things to do with them. One thing that has been made is a satellite communications receiver. Using metamaterials, you can make a very cheap phased array. So normally you communicate with your satellite phone with the satellite by a mechanical dish, which is steered. It's heavy, it's expensive, takes a lot of power to steer it. But you can make a very cheap phased array using tunable metamaterials, and Toyota has put these in the roof of some of its cars. The eventual aim is that Tokyo could be in communication with every one of its cars in the world via one of these metamaterial aerials, tunable aerials in the roof. That was by Meta. Now there's another company called Evolve, which at my last hearing, it's been funded. This figure's out of date. Bill Gates is helping to fund it. He's now upped his stake to $50 million. The company is worth $100 million. And the idea here is to use terahertz radiation in airport security and to a cheap and effective way of scanning terahertz. So instead of going through the terahertz scanning machine, you simply walk past its device. It will undress you and see whether you're carrying any weapons. Another application by my colleague Richard Sims is in a magnetic resonance imaging experiment. And now the idea here is that you have to pick up the very, very tiny magnetic signal from the patient. And if you want a high resolution scan, then the pickup coil has to be very near what you're scanning. So imagine that you want an MRI image of the heart. And what is currently done is you make an incision in a vein in the leg, and the coil is pushed up the vein until it reaches the heart, and there it picks up the tiny magnetic signals. But Richard thought, well, you know, there are some problems with this because there are many different electromagnetic fields around in an MRI setup. One of them is a very powerful RF field, and that can heat that wire. It's connected to the coil, and it can be dangerous sometimes. So there's a little, and also there's another problem, and that is what you're doing is to take the very, very subtle magnetic signal from the little vibrating atoms, and you turn it into an electrical signal. And why do that? Because the body is a very silent, noise-free environment magnetically. So you take this very tiny signal, which is in a very quiet environment, and then you turn it into an electrical signal, which immediately has this wall of noise in the body. So noise is a huge issue in MRI experiments. So Richard had the idea, why turn the magnetic field into an electric signal? Why not design a magnetic wire? And that's what he did to make MRI safer and more sensitive. I mentioned acoustics. Here is a device designed by Ping Sheng. If you live in apartments, you may be troubled by your neighbor making a loud noise. If he plays the bass guitar or the drums, that is particularly bad because low frequency sounds are very good at getting through walls. In fact, in the building trade, there's a rule which says if you want to keep out sounds of a certain frequency, then the lower that frequency, the thicker the wall has to be. But Ping Sheng had a clever idea of making a resonator, which is the acoustic equivalent of the split ring resonators. Here's the resonator. It's a rubber membrane supported on the edge. And in the middle is a weight which determines the frequency of that acoustic resonator. Then you make an array of these resonators. And for example, here's the array put in a tube down which a sound signal is being tested. And you can actually make walls of these resonators, and they're very good at keeping out low frequency sounds. What else? Oh, yes. My former postdoc, Sebastian Guemo, who's a very imaginative young man, has said, what about earthquakes? Earthquakes are waves. And it's the earthquake wave that destroys things. It will be devastating, for example, if a powerful earthquake, the waves from a powerful earthquake hit a nuclear power station. So what can we do? Well, as we've seen, waves can be guided. And here's an experiment being done by a French oil company near Marseille, in which they're drilling holes in the ground to modify the refractive index of the ground to earthquake waves. And here's what they call a thumper truck, which hits the earth and by dropping a heavy weight on it. And then they measure how the sound is deflected by this array here. What else? Yes, so here's some current work going on with metamaterials. You can tune the geometry and so on, but also you can make them time dependent. So they're not only structure in space, but time. And you can do that, for example, by this is using ITO, indium tin oxide, and you can alter the properties of that to radiation by having incident upon it very powerful time-dependent pulses. Here's another application of metamaterials. Two-dimensional metamaterials have become very fashionable of late. Federico Capasso can make lenses which are a few nanometers thick and can focus light. And here he shows how he does that. So these little metallic elements are resonant. They all have slightly different resonant properties. So when the light goes through this bit, it has a different change in phase from when it goes through this bit here. And that's just what you need to design a lens, because the function of a lens is to alter the phase of the light going through it at different places. Anything else? No, I've come to my summary. Okay, so at least I finished within the hour. So I hope I've shown you that metamaterials and transform optics, they're opening new horizons for us. They can produce material properties difficult or impossible to achieve. Can control light of all length scales down to a few nanometers. They've been used in mobile phone antennae for 5G signals. Sub-wavelength microscopy for biological applications is currently being developed. Cheap and efficient control of terahertz radiation, as in collision avoidance radar in automobiles, safe delivery of MRI signals, and last, I haven't talked about for good reason, classified military applications. So sorry to rush things a bit, but there's so much to tell with metamaterials, and thank you for your attention.
John, thank you for this very impressive and exciting talk. That was a great pleasure to listen this Saturday, this talk indeed. Can we now pass to Q&A session, taking perhaps several questions? Please ask questions using a message through chat button or just by raising hand. John, in all cases, these configurations of electromagnetic fields satisfy original Maxwell equation. Is that true?
Yes, it is. Oh, yes.
Or in some cases, one needs to modify Maxwell equations.
Well, I haven't modified Maxwell's equations. I wouldn't dare to do so. No, yeah. Maxwell's equations are obeyed at all times, and we haven't looked at situations where they might be modified.
Yeah. More questions, please. Oh, what about we have one question in chat.
Yes, could you read it out, please? Because I'm still sharing my screen, so I can't see the chat.
Okay, I can read it for you. Can I use metamaterials in coupled resonator formed with photonic crystals for improving transmission? For improved transmission?
Yes, they can do things like, for example, you might want to do something like bloom some structure so that the surface is more acceptable to light. And you can use metamaterials to do that. In fact, blooming is a sort of metamaterial, if you like, because you structure the surface of a lens by putting layers of different refractive index on it, and that's a sort of metamaterial, I suppose. But yes, you can do more complicated arrangements, which which can increase the transmissivity of materials.
So one more question from Fulya. She thank you for very much for this talk, and asking question that how can time varying negative reflection index be achieved?
Whoa, that's asking for everything. At the moment, it depends. If you simply want to retune the negative refraction, so suppose you're doing something more complicated than just a flat negative refractive lens, and you may want to effectively vary the place where the lens is focusing, then you at the moment you can make metamaterials tunable by adding nonlinear elements to them and applying DC fields. So that's where you make them vary on a time scale of maybe a fraction of a second. And that's fairly easy to do. People can do that. What is much more difficult, and what is a focus of, I briefly alluded to, focus of a lot of current research, is to make the metamaterial vary on the time scale comparable with the time scale with the frequency of light. And when you can do that so that the light encounters a structure that is moving as fast as it is moving, then you can have some very, very strange effects. In fact, because those materials are not time invariant, you don't have energy conservation. And once energy conservation goes out of the window, a lot of our assumptions about how materials behave just go with it as well. And that's fun. That's what I'm working on at the moment.
Okay, thank you. More question, please. So if no more questions, so Can, perhaps we can stop here, and please, if you want, give your final remarks on these things. About, please elaborate a little bit on your forecast about the future of metamaterials applications.
Yes.
Should be expanded.
Okay, just a few concluding remarks. It's my philosophy in my research career to, when I'm working on a given topic, I've worked on several topics. My career has been a long one. And I generally have a rule that I try to change topics about every 10 years to refresh things. I've been working on metamaterials for more than 10 years. And the reason for that is that it is the most exciting topic I've worked on. And its excitement derives from the fact that as a theorist, I don't even do experiments in the laboratory, let alone make products. As a theorist, it's very encouraging to see the concept of metamaterials being applied to all across the board to products which is being developed. And it's this long connectivity through the entire scientific and engineering world that makes it so satisfying, and a topic which will live long into the future, I think and hope.
Thank you so much once again.
Thank you.
Yeah, that was honor and pleasure for us.
Yeah.
I hope we will meet in person in future after this pandemic.
Well, yes, let's hope this COVID thing goes away pretty soon. Yes.
Please take care of you this difficult period of time. Yeah.
Okay. Thank you very much.
Bye.
And I'll leave now.
Yeah.